Okay, good morning, ladies and gentlemen. Welcome to today's first panel debate on void reduction, a multidisciplinary approach. It's widely accepted that in the world of void reduction, it's better to have a combination of flux chemistries and mechanical vacuum technology to reduce the amount of voids in the interconnect. I'm joined today by a distinguished panel of industry experts, should I say, to discuss this. To my extreme left, we have Andreas Stemmler from SMT, Wertheim. Then to his left, we have Graham Wilson from Indium Corporation. And to my left here, we have Richard Boyle from Henkel. So welcome, gentlemen, and let's get started. I'm going to start on the end with you, Andreas, and basically ask why are voids, what are voids and how are they formed?
Voids are small gas blasts inside of the solder paste under the products. And when you have a void under a product, this means that the heat can't go out of the product, and this is a point for the lifetime of the product. Okay.
So, Graham, if we take a closer look at the void, you were saying earlier that it's really essentially a CTE mismatch that causes the problems.
Possibly not initially in the design, but as Andrew said, the voiding is a gaseous bubble that sits within the metal mass. So that is more of a problem thermally than it would be for CTE mismatch initially in the lifetime of the device.
Right, okay. Is there a mechanical issue there as well, depending on the location of the void?
Mechanical issues with voids, they can come in play given the CTE mismatch between the device and the substrates that you're using, and whichever design brief that you have for the component itself. So which is its design cycle? What temperature extreme should it have? How many on-off cycles should it have? Those are the things to consider when making your whole design.
Mm-hmm. Okay. Do you have anything to add to that, Richard?
I would just add that sometimes some voids can be beneficial if they're small enough in the right place, because they can act as a stress relief agent. If there is going to be any cracking formed by that CTE mismatch, if it hits a very small void, that will stop the crack from proper gating, so that can then be seen to be a beneficial result. Also, the voiding can add to flexibility within the solder joint. So some voids, don't look at voids as being totally wrong, but also, just to add to what the guys have said about voiding being a gaseous material trapped within the product, you should also look at the shape of the void. If it's a circle, it's definitely a gaseous material trapped. If it's an irregular shape, it could be non-wetting or de-wetting to the component or to the PCB pad. Right. So you should try and identify the root cause of what it is before you look at investigating or improving the defect.
Okay. Right. So, do the panel agree, and I'll start again with you, Andreas, that taking a multidisciplinary approach is the way to do it? It needs to be a combination of chemistry and mechanical vacuum.
To analyze the voidings, you must look at the whole process. So you have the solder paste, you have the thickness of the solder paste, you have the oven, you have the products, and so it's a really complex issue, the voiding, and so this is the reason why we are in this round.
Right. Graham, I mean, using flux chemistry alone, you're likely to get down to maybe, what, 10% voiding, something like that. What's your view on this?
That's putting words into my mouth, Trevor. Voiding is so complicated that it's a multifaceted approach has to be taken to reduce that voiding, but the mechanism for that void to appear in the first place is from many sources. So there are attributes that you can do with stencil design to allow the flux to outgas from underneath the devices. But as Richard's saying, the surfaces that you're trying to solder to can actually be the source of entrapment. Let's call it entrapment rather than voiding. So 10% is an arbitrary number that's thrown around, but it's not necessarily the minimum you can get to, nor is it an average. It's totally dependent on what you're soldering in your process and what's acceptable. And the atmosphere you're soldering within. So sometimes nitrogen is beneficial, sometimes air is beneficial, depending on the chemistry that you have.
Right.
Typically SMT, I mean, people are still looking to the under 25% for typical applications, but some more challenging, more high reliability, aerospace, automotive, they're challenging that rule for different packages. So new numbers are appearing, which is why we're traveling from Richard and myself's side to the equipment side as well. So they come together.
Yeah, yeah. You make some interesting points there. I mean, what's your view on stencil design? I mean, it has a contribution to this as well.
I think, as we said, because it's such a multifaceted root cause of what the voiding can be, definitely stencil design has an impact on reducing the voids. By introducing a railroad-style aperture for large area heat sinks, you can drastically reduce the amount of voids. It depends on where the voids are. We shouldn't just concentrate maybe on the thermal side. You've got the voids in BGA. I think everyone would agree that's pretty much under control now. We're all happy that most voids on BGAs are less than 15% and generally are approaching the less than 7-10% that most people are actually aiming for. I think one of the issues we have here is the IPC is relatively sketchy. BGA is fairly well established. Everyone knows what you need for class 1, class 2, class 3. For the other parts of the board, voiding isn't clearly defined within the IPC. And I don't think it's clearly defined within industry either. I think there is more of a specification from customers, what they would like to see. And customers are looking for something that's nice and pretty and may not really be specifying what is necessary for the actual product to work. But on a good day, everything in the right place, everything working well, I would say with a solder paste, you can definitely get down to about the 10-15% voids on a regular basis. If you want to go less than that, I think you need to start to look at using preforms or more exotic systems to maintain that much lower result. And we were talking beforehand, with a good preform, you can get less than 0.5% and a vacuum system on a regular basis. But you have to work hard to achieve that.
So that's the lowest you can get down to, is around about that area using the combination of preforms, chemistry, and vacuum. What numbers are most customers asking for? I'm hearing less than 5%. That's the number I hear, but I mean...
I think if you want to know what the result the customer wants, you need to get a 30-sided dice and roll it, and the customers will then vary.
And then half the number.
Yeah. Okay, all right. Andreas, back to you. Looking at vacuum technology in reflow ovens, what steps does the operator need to do to ensure he's achieving maximum results? I mean, he doesn't just put it in there. I mean, what things does he need to do?
Yeah, we developed the reflow oven system in 2009, and since that we have made a lot of tests about the maximum reduction of the voids. And so you can, for example, play with the pressure inside of the vacuum chamber. Mm-hmm. You can play with the time to to go down with the pressure, and you also can have a holding time inside of the vacuum chamber to minimize the voids.
Okay, but typically your vacuum chamber happens at the area of the oven which is where you do peak reflow. Is there an issue there? Is there a trade-off there between peak reflow and the exposure time that you have with your vacuum?
Sorry, could you repeat it?
Well, you've got peak reflow, which is in the same area of the oven where you do your vacuum. So is there a trade-off between the amount of time that you have the vacuum applied versus peak reflow? Because you have to be careful that you don't go over the top.
Inside of the chamber, the product is standing, so you have a little holding time inside of the chamber, and the peak gets a little bit longer as in a usually soldering process in a reflow oven.
Right, okay.
You could Can I just add something there? I think generally from a voiding point of view, if you're looking to reduce voids, you want to make sure that the materials that are going to evaporate have evaporated before you reach that reflow point. Because once the solder melts, you then have an issue with the surface tension of the alloy and getting the gas, the liquids out of the material then. So really, when you're designing your process, your profile, you want to make sure you understand the chemistries involved and that you've managed to evaporate as much material or moved it out from under the component before you reach that reflow stage.
Okay, okay. So so really what you're saying is get rid of it before it gets to the peak reflow area. Do you need to change, do you have to use a different type of profile when you're using vacuum?
You have to change the profile because you have the time of the over liquidus, and this should be is defined from the solder paste supplier. For example, 1 minute, round about 70 seconds, and so you must change the profile with the vacuum system.
Okay, okay. Graham, are there any other points that people should, manufacturers should consider when looking for a solder paste that they can use, for void reduction?
Certainly, from my side, is that make sure your design is according to what you want to achieve at the beginning. The times that you will then find a challenge is the variation in your production items, so the PCB, the profile, the temperature, the variables that will come in the production. So make sure that you've got a solder paste that's robust enough to cope with changes in your process that you need to make based on the components that you're reflowing. It's got to be stable enough to go through a short profile, long profile. It's got to have enough of the chemistry that's activated and exhausted before you get to peak temperature. Make sure you can go higher in temperature if you need to reduce oxides further. So it is a combination of the whole chemistry there that's gonna really give you the widest operation window for your design.
Okay. Richard, Henkel specializes in doing a lot of long storage life pastes and things like that. Are they suitable for using in void
Historically,
reduction?
no. I think when we first launched the very long stability room temperature storage product, one of the things that came out of it was the amount of voids that were there. And that's inherent in the design of the product because the flux chemistry is so stable. It's very difficult for it to evaporate during the initial reflow process, and that could lead to extra voids. Certainly there's been some developments since then. There's been some chemistry modifications. New products have been launched that are designed specifically to reduce the amount of voids without impacting on the storage capabilities. But looking at the chemistry, and I think Graham will agree with this, looking at the chemistry of the solder paste, if you could design something that can give you exceptionally low voids, but you then take away some of the benefits from the print process and maybe from the tackiness to be able to hold components in place.
Right.
So you need to weigh up those balances too, as Graham said, to have the wide reflow process window, the short reflow process windows. You need to have the chemistry there that can cope with everything. So sometimes there is a small sacrifice there. Again, I would say, I think all of us in the development side have developed products now that are specifically designed to help reduce voids. Mm-hmm. And certainly from the ones that I've seen, they all have very, very capable print process windows, reflow process windows. And we are edging that voiding level down now. Five years ago, you would have said that 35 to 50% voids on large area pads was what you were going to get without the use of vacuum.
Yeah.
Now you can look at the 15 to 25% as being achievable without vacuum, but then with the addition of vacuum processing, you can drop that down to the sub 10% very easily.
Right. Okay, well, I'm more or less out of questions on this, so I'm going to open this up to, is there anybody in the audience that's got a question for our panel? Do we have an extra microphone, or can we? Here we go. Take that one. No, we've got one. Okay, we're just going to wait for.
I must take yours. Thank you.
Okay. Okay, just Thomas, if you can just state your name and company and ask the question.
Yeah, it's Thomas Stetter. I'm head of assembly solution, Micronic. I would be curious, interesting discussion, I would be curious, is there any research on the influence of stencil printing versus jet printing on the amount of voids?
Good question.
I think there is a difference there, obviously, because the jet printing, you're jetting dots, so there is a potential you're introducing on a large area some larger amounts of air trapped between those dots. Certainly with the stencil printing, there's been a lot of work done to look at aperture design, to look at reduction of voids, and I think that's quite well established now. With the jetting systems, the work we've done has shown that it's a lot more stable. There's a lot less variation in what you get. And because you can, in some ways, improve the thickness of the solder, you can regulate the amount of voids by purely the volume of solder that you're putting down. So there is some work maybe to show that, but I think I would agree that there needs to be a lot more work done to establish what trends there are and what benefits there can be from the flux chemistries and from the design, the jetting pattern that you use. And I think the flexibility that you get from the jetting system enables you to be able to do that on the fly, not wishing to, you can midway through doing a production run, you could potentially change that parameter and you could look at what the results are.
Yeah. Okay. Graham, do you...
For me, I agree as well. We're involved in the jetting side, and we do see lots of development work, and we see the comparisons between all the stencil designs, and it is the opportunity to have that flexibility in a production situation for doing that is probably more versatile, but we don't yet know which patterns are good for which components in which situations every time.
Okay, great. To answer your question, do we have any other questions from the audience at this point? No? Well, great. Well, I want to thank our panel once again. We've had a great debate today. Andreas Stemmler from SMT on the end. Then we have Graham Wilson from Indium Corporation and Richard Boyle from Henkel. And thank you for joining us today. Thank you.